Quantization solution to the ultraviolet catastrophe. Classical physics was used to explain the principles of kinematics, buoyancy, forces, waves, electricity, and magnetism. Basically everything you learned in high school physics. During the 1800s, classical physics had initiated the Industrial Revolution, allowed for the use of electrically powered objects, and led to the realization that light was composed of electromagnetic waves. With more resources available to science, physicists wanted to try and understand why hot objects emit light. Although this seems simple, classical physics could not explain the phenomenon. Before we explain the phenomenon, a quick physics review is necessary. When particles absorb energy, they begin to vibrate with distinct frequencies, and these particles were believed to emit this energy in the form of light as electromagnetic waves. Any waves emitted within the visible light section of this spectrum could be detected by human photoreceptors, while waves with other frequencies can be used for other purposes, such as radio waves, which are used in an MRI. It is important to note that all waves within the same medium, such as a vacuum or air, will travel at the same speed. Therefore, if all the waves on this spectrum have the same speed, they must have inversely proportional wavelengths and frequencies. This can be proven with the equation seen here. For example, radio waves have very long wavelengths, but very low frequencies. Black bodies are objects which can absorb and emit light at all wavelengths. Objects can emit, absorb, or reflect light, but perfect black bodies do not reflect any light. Such examples include iron when heated or the sun. Classical physics believed that as energy, like heat, was put into atoms, they emit radiation at increasingly higher frequencies, which makes sense intuitively, because if you heat up molecules, they vibrate at faster frequencies. So the temperature and radiation signal intensity should be directly proportional. Therefore, physicists use this equation to predict what the signal intensity would be from the emitted wavelengths observed from black bodies at different temperatures. What the physicists discovered was that although black bodies emitted a range of many different wavelengths, they did not increase exponentially. Their first test used a 3000 Kelvin black body and showed a peak signal intensity occurring just before the visible light wavelength section. The next two experiments used hotter black bodies and showed the same type of functions with peaks in the visible light wavelength section. Although this experimental data disagreed with classical physics, there were two visible trends. As temperature increased, the area under the curve increased. This explains why hotter objects give off more light, as the area under the curve corresponds to the amount of waves emitted. For example, the hotter a piece of iron is, the brighter it glows. Second, as the black bodies grew hotter, the peak wavelength emitted shifted to the left. The left shift explains why we see the iron change colors as it is heated up, from red to yellow to white, since the peak represents the highest number of waves at that wavelength emitted. Then the point on the visible color spectrum where the peak is will determine the color we see. To solve this issue, Max Planck developed this new equation and plotted theoretical data on points on a grid for a black body of 4000 Kelvin. His points lined up almost perfectly with the previous experimental data. Don't worry about all the variables of this equation, since from this we can derive this much simpler equation. The change in energy is equal to the frequency of a wavelength times Planck's constant. After proving that this equation was the mathematical basis of the experimental data, Planck developed a theory. Planck's idea is that energy is quantized and not continuous. Therefore, the value of energy by which molecules can increase is equal to the frequency of the wave emitted times Planck's constant, an experimentally determined value. So energy increases in very small steps, like a staircase. However, the variable h, also known as Planck's constant, is very small. This explains why quantization was never noticed before, as it was too small to notice on a large scale. For example, take note that as the staircase gets smaller, the difference in energy are harder to view. We know that subatomic particles vibrate at different frequencies and emit different frequencies of radiation. And Planck believes that energy is not shared equally by subatomic particles that vibrate at differing frequencies. Planck believed that energy is absorbed and emitted at certain quanta of value, not arbitrary values. You can see from the picture on the right here that each red dot has a change in energy between them, and subatomic particles can theoretically only hold these values of energy. The energy of the quanta is dependent on the particle's vibration frequency. Particles which vibrate emit energy as light, which we know as electromagnetic waves. So a particle without at least one quanta of energy can't produce any light. At higher frequencies of vibration, the quantity of energy required to increase to the next energy level is so large that the high-frequency vibrations cannot start vibrating. In order to have any light emitted from the blackbody, the subatomic particles within the blackbody must be shaking with the specific frequency required to increase to the next energy level, as we see in change in energy times n times h times nu. This means that eventually, at a certain energy level, there is not enough thermal energy within the blackbody to induce the vibrations at the frequency required for an increase in energy. Therefore, waves with very short wavelengths are not able to be generated, and the blackbody spectrum shortens on the left-hand side. The significance of Planck's research was not that he had discovered why black bodies glowed when they grew hot. It was that he had discovered energy was quantized. The classical physics era was now over. Quantum physics had begun. People didn't care at the moment because a lot of people thought he didn't have enough proof to back his theory, but Einstein would go on to define Planck's quanta as photons. The image on the right shows the spectrum of wavelengths emitted by the sun. You can probably see that the peak of the wavelengths occurs in the middle of the visible light spectrum. This isn't coincidental. Since these wavelengths have the highest intensity, human eyesight has evolved to recognize the colors in that spectrum. One practical application of quantum physics that would arise in the 20th century was the invention of the MRI. In an MRI, protons in the tissue being examined are excited to a higher energy state, and when they fall back down, energy is released and used to generate an image. Let's try a sample question to help you understand. In an MRI, protons are excited to a higher energy state by a radio wave pulse with a frequency of 42.8 megahertz. What is the difference in energy between the two energy states? Pause the video and see if you can figure it out. Okay, had enough time? For this question, you first need to convert megahertz to hertz by multiplying 42.8 by 10 to the power of 6. The product of this number times Planck's constant is 2.83 times 10 to the negative 26 joules. As mentioned before, this change in energy, one step up the staircase, is very small and could not be detected by humans without biotechnology brought on by the field of quantum physics.